First, to review what we discussed the last time. So essentially, last time we discussed a few things, which is we have the expanded both the wave function and eigenenergy in terms of these terms. So we have zeroth order, first order, second order, and keep on going. And then we also have energy exact same. First order, second order, and keep on going. And then we say that we're going to plug this guy back into the equation. So that's on page 130. So that's where we are. Folks, let's go back to 134. So let's go turn to 134. And we're going to show you a little more detailed, and which we will do the calculation. So 134, and today we're going to have to 135 now. Let's move on 135. So this is another page, so that we will work on that. And so before we do that, I want to show you two key things which is involved. So this is step number 1, that's what we did, and that's step number 3. Step number 4, I just want to show you the step number 4. These just are key steps. And then we're going to read the book, and I want to show you what we will do. Step number 4, it contains 2 steps involved, essentially. And the 2 step which is involved is the following. First one, we will multiply by phi, have exactly the same index as we had before. So in other words, we multiply by the k, exact same k. You remember, this is eigen state which we only can solve. So eventually, we multiply by the k like this. So that's the one which we have. Second, we will multiply m. M not equals to k. And this is the steps you're going to see me going. In other words, we're going to multiply. Let me complete the entire sentence so that way you will see what I meant. So this is the entire sentence. So we're going to multiply from these, from the left and integrate. So that's the key steps. So one case we multiply by psi k, the other case multiply by psi m. And that's we will do. And you may wonder why we need this. So you're going to see immediately why this comes out. Remember, it's a very simple step which we started. We will multiply by same index as we are interested in. The other one is not same index. So they are the difference. So the first person to read is the Toby. Toby, could you read 5.1.1, 5.1.3.1? Stuff like this. Yeah, first order energy correction.
Do you want me to read out the...
Yes, please.
Multiplying equation 5.1.8 by phi sub k. From the left and integrating, we have direct notation of phi k h hat sub naught and phi k to the first order, plus direct notation of phi k with the operator h hat I phi k, which equals epsilon k, direct notation phi k, psi sub k to the first order, plus e sub k to the first order, phi of k, phi of k.
Great. Hold on 1 second. Are we on the same page? We are starting from equation 5.1.8. Both sides multiplied by when we use direct brackets and angle brackets, both broad and k. This means integral. Okay, so Toby, this means integral. So that's what we're getting now. And then then all these terms comes naturally like this. Could you continue, please?
Using 5k h hat sub naught equals epsilon k 5k, and canceling terms with epsilon k. We have the first order energy correction. E sub k, so the first order equals direct notation of 5k h hat I h 5k. This shows that the first order energy correction is the expectation value of h hat I in 5k.
Great, thank you so much. Are we good from equation 5.1.9 to 5.1.10? Are we good? Everybody's good? So could you give me a thumb up if everybody's good? So just remind you, the cancellation happened, the first term on the left-hand side in equation 5.1.9, and first term on the right-hand side, these two terms cancels out. So that's why these two removed. Then the first order perturbation, and we also use the normalization. So this is normalization. We also use normalization. This guy equals 1. So that's why you can see the left-hand side. The left-hand side we have E, K, hat. So the right-hand side is just integral of this particular part. So that's why you see the average value of this term comes out. So the next step is really doing this part. Okay. Cody, could you read the next section, please? Subsection.
Multiplying equation 5.1.8 by star and not equal to k from the left, and then integrating we have phi then h sub I bar phi k equals epsilon k minus epsilon m phi then psi of k to the first order, which gives phi sub m psi sub k to the first order equals thought is phi m h sub I bar phi of k equal all over epsilon k minus epsilon m, which is all over not equal to k.
Okay, hold on one sentence. From equation 5.1.8, we just left multiply by phi sub m star, and then are we understanding from 5.1.8 all the way to 5.1.11? Do we understand that term? I jumped that slightly. And I want to show you what that's. It's not obvious, right? It's not obvious. I'm going to plug in this particular step. All right? Can I plug in this step? So I'm going to plug in this step because from 5.1.8 to 5.1.11, it's not obvious because there is a missing gap there. So this time I'm going to insert this one over here. So I'm going to let me erase this part. This is quite important because I don't want to overlook this. And I want to erase this part. And this particular equation is quite important. So which one we used. So here is one step which is quite important. Then you copy that equation down here, so that way you will be able to see. So this is the 5.1.8. Could you guys write this down? H naught psi k, and this h hat phi sub k equals epsilon k pi k plus e pi k. And then we have phi here like this. So this is the one that we had before. So this is the equation. Now we say that we're going to left to multiply by phi sub m. So this will left to multiply by psi sub m. So this will be interval. Same thing here. This is left multiply sub m. And here's the same phi sub m. And left to multiply. And this is the same thing here. E k left to multiply sub k like this. I prefer to write them out completely. Let me write on this line. That looks. I just want to be real precise. Okay. second term. So that way, it's quite important. I don't want to skip any step whatsoever. So here is this term. And this is a constant. I can move them out. So essentially, what I do, epsilon k, phi sub m, beside k, 1. And now this term is also constant, so I move them out. Okay, like this. So this is the one we have. So this is a complete step, which with the left-hand side will multiply by phi sub m. Now what we do here is the following. Did you see this term is 0? This term is 0. Is it because we assumed my m not equals to k? So therefore, this term here, this term is going to be 0. Now, this term here, so this term is 0 because m not equals k. Remember, this particular step, my m never equals k. So that's what we assumed. Now here, this part, this is left applied h0. This gives me e lowercase epsilon m, and this will be m like this. In other words, the bra phi sub m and h naught applied on this will be equals epsilon m and a bra. So that's that. And then we have a k equal this term. So, so this term is going to be 0, and this term becomes like that. The middle term we cannot do with anything with that because there's no way to simplify it. Phi h naught phi k epsilon k phi m psi k, one like this. So that is what we have. And this equation is closer to our the textbook equation, but not completely same. What I did was we're going to move this term to the right-hand side. Did you see? These two parts are exactly the same. So these two parts are exactly the same. There's no difference. And this part, so I combine these two together, and so that is what we have. That's right. So we'll combine these two together. That's a phi m h hat phi k. So this will be epsilon k minus epsilon m, and then phi m psi k like this. So this is what we have here. So this is a step in the textbook which is missed. So from here all the way to there. This is equation 5.1.11. So that's equation 5.111. This is much clearer? Okay, Toby, is that clearer now? So this is all the steps that you needed from going from here, there, and all the way to this. That's why I don't want to jump so quickly. So this is a step, and we have, and then when we solve for this, just both sides divide by this factor. So therefore, phi and psi k just equals phi m h hat phi k epsilon k minus epsilon m. So this is what we have here. So this is the final equation, which is so crucial. You can go over that. That's a really important in this case. So this is a very important. Toby, you got a question for me? Yes.
So is h hat sub I like in a form some type of ladder operator?
This is not defined yet. This is not defined yet.
Okay.
So in other words, until we know what this form looks like, we have to leave as it is.
Okay.
And while the eigenstate phi belongs to h0, so you can simplify it right now. but not the other terms. That's is stuck over here. So there is no way until we show you the real concrete example and you'll be able to see that. Yes, that's what that. Any other questions? Any other questions? Okay. All right, Cody, whenever you're ready, let's continue read that.
What was that? This represents what that?
Yes, exactly.
Oh, okay. This represents an overlap between psi k to first order and phi sub m, and means that the first order perturbed wave function has continuous from eigenstates other
Has
than
contributions.
has contributions from eigenstates other than phi sub k. We have to include all the eigenstates phi, which is why we emphasize that we need to keep index I for phi to have a correct psi sub k of the first order. We must add them up to see this clearly. Replace the completeness of eigenstates sigma m of phi of m equals 1 before psi of k.
Okay, hold on 1 second. So this part I want to explain this really well, and I hope my camera can see this. Yes, it can see that. So what we did following is this. Folks, could you guys leave some space here? The first order wave function correction psi to first order sub k, it must be equal sub k. Why? There's no question because they are the same thing. Then what I did was we plug into the number 1 here. 1 times the same thing, there's the number 1 here. And then we replace this 1 by a normalization condition, which is this. We change the normalization condition, we change this to this. Phi m. Let me write a little wider space, I don't want you too small. So what I did was, this is the completeness relation. This is the complete relation. In other words, this summation equals 1. We did it in the particle box. Actual particle in a box is the only one that we can verify. The rest of it is kind of crazy. We have to believe that's true. But this is what happens. This is so-called completeness. There's nothing strange about this. There's completeness involved. So now once we plug it into it, then you will see this part. Now this part is a magic in the sense that before you write, there's no integral, but when you plug it in, this part becomes an integral. This integral is the coefficient on top. That's why we get a perturbation function. So the entire wave function is going to become to look like this. Now m cannot be equals k. This cannot be equals k. Now in the beginning, here's equals k, but after this, it cannot be equals k. That's what we decided this. So then you will have this bunch of this coefficient, phi sub n h hat phi sub k, and then we have denominator k minus epsilon n. So this is what we have. Now we still have this guy that remains, so therefore you can see that n. So this is a number now. This part is a number, this is a number, and I have wave function mode to the behind here. So that's how the perturbation wave function is determined. Yes, you can see clearly here. So this is how the perturbation wave function is determined. And before we move on, let me summarize what we did so far. The first order energy correction, the energy is a diagonal element. You see, energy is a diagonal element. But a wave function is an off-diagonal element. So you see, n cannot be equals k. So that's the difference. So the first order wave function is off-diagonal, but the energy first order is diagonal. So that's the difference. You remember that. That's the key difference. I'm going to summarize this on board before we move on to the next. So this is quite important conceptually. So we're going to summarize what this is, so that we can remember it easily. Here is a summary. eigenenergy correction, first order, energy correction is diagonal. First order wave function, I simply use WF correction, is off diagonal. So you can remember the first order wave function correction is off diagonal, which as I showed here. So that's the key difference between this ones here. Now, in order to remember this, it's not easy, right? So that's why Feynman created these kind of Feynman diagram in order to remember all of these features, which you're going to see them. Okay, so that's expression. Cody, could you continue to read the next line after equation 5.11?
Since m does not equal k, excuse me, sorry, and 5 sub m and 5 sub k equals 0, 5 sub k with the first order is orthogonal to 5k. Equation 5.1.13 means that the wave function correction is a linear combination of perturbed eigenstates 5m, but it is weighted by the coefficients 5m h sub I bar 5k all over epsilon k minus epsilon m. If a state's unperturbed eigenenergy epsilon m is closer to our targeted state's eigenenergy epsilon k, it has a larger contribution. The unnormalized wave function up to the first order correction is psi of k equals psi of k to the 0th order plus psi of k to the first order equals phi of k plus sigma m does not equal k of phi of m h sub I bar phi of k all over epsilon k minus epsilon m and phi. To normalize it, one can compute psi of k, and rescale it psi of k over the square root of psi of k psi of k.
Great. Thank you so much. Thank you so much. So that's the end of the first order. Do you find it complicated? How many say not complicated? No, it is very complicated. You see that? That's why perturbation theory, not people like it, because you have to do some subsequent terms. Now, this is just first order. And Alex, let's read the second order together. The key idea is identical, exactly the same. You can keep on reading that. Yeah, just section 5.1.4.
We can start with equation 5.1.5 in mass terms of m squared h naught hat phi sub k plus h sub 1 hat
H sub I.
h sub I hat phi sub k equals e sub k phi sub k plus e sub k phi sub k plus e sub k phi sub k for 0 to 1 1 0 equals epsilon k phi sub k 2 plus e sub k 1 phi sub k 1 plus e sub k 2 phi sub k, which shows the second order.
Hold on 1 second. Do we understand the equation 5.1.15? Do we understand? Any questions on that? So the first line in equation on the right hand side, did you see e sub k superscript 0 order and second wave function is 2? Did you see that? So in other words, if you add these two superscripts, add them up, you always get 2. Did you see 0 plus 2, you get a 2. 1 plus 1 gets 2. 2 plus 0 get 2. So you know that whenever you see second order, the orders themselves, add them up, all of these terms will be exact same. So it's very easy to remember. That's why Richard Feynman was able to determine which order you actually have. That's why I created this Feynman diagram. Because these orders are fixed. And then all these orders will be linked through these kind of indices. That's the key idea. The next equation is just using the previous knowns, which is the 0 orders is psi k, epsilon k, and then that's why I keep on going like that. Yeah, keep on going the next sentence, please, Alex.
So it shows the second order correction and the first order correction in such a hierarchy is the hallmark of perturbation theory. And many procedures have assume it's first order 1.1, second order energy corrections.
Oh, hold on. I would like to ask Aisha to read this. It's a little bit too much. Yes, go ahead, Aisha.
We also left multiply equation 5.1.15 by phi sub k and integrate to phi phi sub k h hat not psi sub k to the second order plus phi sub k h hat to sub I psi sub k to the first order equals epsilon k times phi sub k phi sub k to the second order plus e sub k to the first order phi sub k psi sub k to the first order plus e sub k to the second order phi sub k phi sub k. Using phi sub k h naught equals epsilon k phi sub k, we can cancel the first terms on both sides of the equation. The second term on the right is 0 because phi sub k psi sub k to the first order is psi sub k to the first order is 0 due to equation 5.1.13. Employing the normalization condition phi sub k equals 1, we obtain the second order energy correction as e sub k to the second order equals phi sub k h hat sub I phi sub k to the first order.
Great, thank you. Hold on 1 second. Any questions at this step? Okay. So did you see 5.1.13? That's equation in the previous page because that's, you remember the correction is to orthogonal to the k itself. That's why this part equals 0. So this is a quite crucial. Toby, could you read the next paragraph, please?
To appreciate one.
Yes.
To appreciate the beauty of perturbation theory, we pause here to explain the structure of e sub k to the second order. The entire expression is just like the expectation value, but the wave function on the right is replaced by the wave function, which is 1 order lower. Our first order energy correction is e sub k to the first order equals Dirac notation phi sub k h hat sub I psi sub k to 0 order. If we compare the structure of these two equations, we find that they are similar. This nice connection is hidden if we replace psi sub k to the first order by phi of m. So e sub k to the second order equals the summation when m does not equal k. Dirac notation phi sub m h hat sub I phi sub k times the Dirac notation phi sub k h hat of I phi sub m all over e sub k to the 0 order minus e sub m to the 0 order, which also equals the summation when m does not equal k of Dirac notation of phi sub k h hat of I phi of m times Dirac notation phi of m h hat of I phi of k all over epsilon k minus epsilon m.
Okay, very good. Thank you so much. So, in other words, the equation 5.1.18 and 5.1.19, these are standard the other textbooks used. In other textbooks you will see like this. It's just not crazy. You have to remember the whole thing. But it turns out when we start to write a book, essentially these expectation values on the left-hand side is the original ones. Right-hand side is the order above. Right hand is order above. Right hand order above. So that's what it is. Okay. Cody, could you read the next paragraph starting from 5.1.4.2?
We multiply equation 5.115 by state phi star m is not equal to k from the left and integrate it to get epsilon m phi m psi k to the second order plus phi m h sub I bar hat psi k to the first order equals epsilon k phi of m psi k to the second order plus ek first order phi m psi k to the first order plus ek to the second order phi m phi k, which yields the overlap between psi k to the second order and phi m. Phi m psi k to the second order equals phi m h sub I hat psi k to the first order minus ek to the first order, phi m psi k to the first order, all over epsilon k minus epsilon m. Here we have used phi m does not equal k, phi k equals 0, since epsilon m is closer to epsilon k. This overlap is larger, similar to psi k to the first order. Phi m does not equal k is not the only state that contributes to psi k to the second order, but all other states do. So we sum up all possible states to get our second order wave function correction. Psi of k to the second order equals sigma of m does not equal k, phi m h sub I hat psi k to the first order minus epsilon k to the first e k to the first order, phi of m psi of k to the first order all over epsilon k minus epsilon m. What's the recognition of phi of m? One sees that it depends on the first order, psi of k to the first order, and e of k to the first order. For this reason, its expression is rather cumbersome.
Great, thank you so much. All right, now you enjoyed all the complexity of the perturbation theory. That's why a lot of people, well, I don't like that much because that's perturbation theory, so you one at a time. Okay, now let's go back to the business, to what we actually could do with this. So this is the new section, so which will talk about examples. In other words, I'm going to move my camera over this side here a little bit. So this time we're going to talk about some examples. Can I erase this part? Did you guys write this down already? You know, with the first order. And this is the one which we're going to do now. So now we're going to move on examples. The first section essentially is just showing you the theory, but how to use them. So this is example. Section 2, example. There are very few books actually that have one section completely dedicated to examples. And when we started writing a book and we realized this was so important and so incredibly really nice. So we have two examples. So this is the first example, is on page 137. So this example, and so this example essentially has some kind of key features, but I do want to ask Alex, could you read the first paragraph under section 5.2, examples of non-degenerate perturbation theory?
Non-degenerate perturbation theory network will represent two major examples. The first would like to highlight key steps. Separate the system Hamiltonian into two parts, H naught hat and HI hat, where H naught is on solution and HI is small in comparison to H naught. Choose a targeted state K of interest, construct the matrix elements of H sub I hat along the eigenstates of H sub 0 hat. Compute the energy correction of the wave function.
Great, thank you so much. This is excellent. So the first is a harmonic oscillator. This harmonic oscillator has the it's so different. It's a non-neutral. It's called a charged harmonic oscillator. Essentially, we attach a charge to the harmonic oscillator. So this harmonic oscillator, of course, is charged. So that's why we will have these two different terms, which is quite important. So the entire Hamiltonian, and we place this harmonic oscillator in an electrical field. So place them in electrical field. This is not some kind of artificial problem. No, it's actually a realistic problem in many ways. For instance, suppose I have, let's say, the hydrogen atom. So here's a hydrogen atom, or maybe some kind of molecules. So suppose this is the atom number 1. Here's atom number 2. So you can assimilate the vibration in terms of the spring constant, and then you apply electric field, and then you notice that these will be shifted over. So that's electric field. So that's why Hamiltonian has two parts. H naught is the original Hamiltonian for the harmonic oscillator. H hat I is the electrical field which is applied to that. So our H naught just equals T plus V, and this is just the kinetic energy terms, which is P hat squared over 2m. So that's the kinetic energy term. Plus potential energy 1/2 m omega squared x squared. Folks, let's change to P to Px. We just think about one-dimensional, and that's the equation which we have. So this is the one which we know before. That's the harmonic oscillator. Now H hat, and this one we never encountered this. How do you describe the electric field or the charge in the electric field? Here's what we do. Suppose this charge is called Q here. Then if you apply the electrical field, let's say around this direction, it will have the energy due to the electric field. This E is nothing to do with energy, it's just electric field. This E, and then this is what happens. The classical simulation, in a classical mechanics, or E&M, so this is actually the E&M. In the E&M, the interaction between the charge, you will have extra terms comes out. So this is an extra term, which is the D is a dipole. This is a dipole moment. E is electrical field. Electric field. So this is electrical field. And this is extra energy terms like this. Now, in quantum, when you go to quantum mechanics, this term is going to represent it by an operator, H hat, exact same. So did you see I have a D here? This D will become operator. So that's a quantum mechanical operator. E is not an operator. So in other words, just be sure, we treat the charge quantum mechanically, but electrical field classically. Let me write this down. We treat the charge quantum mechanically, but the E field classically. So this is the Hamiltonian which we are using it. We treat the electric field classically, but the system or the charge itself quantum mechanically. So that's the difference which I'm talking about right now. So this is the big difference in the sense that we treat the delta E quantum mechanically, but E itself, also D quantum mechanically, but E is classical. In order to treat E quantum mechanically, we just all needed to quantize the electric field, which is just rather straightforward. Just put them A plus dagger like this. I'm not going to go over that too much because it's just a very small terms here. So therefore, my D will become like this. So my Hamiltonian is going to be minus D hat E like this. So that's what we have. Now, what about this D? And you remember in classical physics, this D, so the classical physics, this D is just charge times the location of the charge. So that's where it's situated. So location of charge, that's what we have. In one-dimensional, we just like times q times x. That's a one-dimensional. So in other words, if the one-dimensional, we will write this particular following format. Then if you have our Hamiltonian, this essentially will be negative q x, this is quantum mechanically times E. Because I do not want to confuse with electrical field, that's why in the book we use the letter F to write them down. Because otherwise you have two E's, and when we talk to the publisher prefer to use the F. So anyway, I think it's a good idea, because otherwise students get totally confused. Electrical field have E, and so we use F. So just remember, this F is really the E, same thing. But when we type, sometimes when we correct them, it becomes much harder to do it. So this is the key idea which we have, like this. Okay. Are we good so far? Now, that's where the Hamiltonian, we're going to split in this following fashion. All right. So now we can read it, the solution. And actually, could you read starting from page 137, 5.2.1, charged harmonic oscillator? Start with one-dimensional.
A one-dimensional harmonic oscillator carries charge Q and is placed in an external electric field F, not to be confused with energy E. Compute A, the energy correction up to the second order in the electric field, and B, the wave function to the first order. A, since the electric field is weak, we will treat it as a perturbation. The total Hamiltonian of the system is split into two parts. H hat equals H hat naught plus H hat sub I, where H hat naught is the unperturbed harmonic oscillator Hamiltonian, and H sub I is the interaction between the electric field and the system, i.e. H sub naught, H naught equals negative H bar squared over 2m, d squared over dx squared, plus 1/2 m omega x squared, where H sub I equals negative d.
Okay, hold on one second. There's a correction. Did you see omega? Should be omega squared. Yeah, I did not realize. Could you guys correct them if you have physical books? This should be omega squared. Yeah, this is the mistake. I need to write this down. 138. Yeah, even though we check very carefully many times, but still carry some kind of typos. You should have omega squared there. Yep, that's it. Aisha, could you keep on reading?
Here D is the dipole Qx, and A sub I equals negative Q times f of x times x. The eigenvalues and eigenstates of the unperturbed system are E sub n to the zeroth order equals n plus 1/2 h bar omega, and phi sub n denoted as n. Non-degenerate perturbation theory handles only one state at one time. Since suppose we are interested in state K with energy up to the second order, E sub K equals E sub K to the zeroth order plus E sub K to the first order plus E sub K to the second order. The zeroth order energy is E sub K to the zeroth order equals K plus 1/2 h bar omega. Next, we compute the first order correction, which is given by the expectation value of H sub I in the zeroth order wave function. E sub K to the first order equals psi sub K to the zeroth order. H sub I psi sub K to the zeroth order equals K H sub I K equals negative Q F sub X K X K equals 0.
Okay, I'll stop here, please. Thank you so much. Do we understand the entire results? First order perturbation, the energy equals 0. Because if you have you guys remember if you have an eigenstate in the harmonic oscillator, if the position operator is x, and that expectation value is 0. So in other words, that's what happens. You guys got it? So that's the main reason. Okay, Toby, could you continue on that where we have used?
Where we have used direct notation K x hat K equals 0 for the harmonic oscillator with no contribution from the first order perturbation. So we need to compute the second order energy. E sub K to the second order equals the summation when n does not equal K of direct notation K h hat sub I of n times the direct notation in h hat sub I of k all over e sub k to the zero order minus e sub n to the zero order, where the summation excludes n equals k. In order to compute e sub k to the second order, we first calculate the direct notation k h hat sub I of n, or 2n, equals negative q f sub x times direct notation k x hat of n. Since x hat equals the square root of h bar over 2n omega times the quantity a hat plus a hat dagger, then x hat of n equals the square root of h hat over 2n omega times the quantities of square root of n minus 1 plus the square root of n plus 1 closed quantity. We have the direct notation k x hat of n equals the square root of h bar over 2n omega times the quantity, the square root of n times the direct k in n minus 1 plus the square root of n plus 1 times the direct function of k n plus 1 closed quantity, which yields all of that.
Okay, all of that continues by Cody. Cody, could you read that long equation, please?
Okay. E sub k to the second order equals sigma of n not equal to k, q f of x squared times k x hat n and x hat k all over h bar omega times k minus n, which equals qf f sub x squared over h bar omega, which times k x hat k minus 1 times k minus 1 x hat k all over k minus k minus 1, and then all that plus k x hat k plus 1 times k plus 1 x hat k all over k minus k plus 1 closed quantity. Since k x hat k minus 1 equals square root h bar over 2n omega root k, and k x hat k plus 1 equals root h bar over 2n omega root k plus 1, e sub k to the second order equals negative q f sub x squared all over 2m omega squared. Our final energy for the level k of the second order is e sub k equals k plus 1/2 h bar omega minus q f sub x squared all over 2m omega squared. This shows that the energy spectrum is downshifted by qf sub x squared all over 2m omega squared.
Thank you so much. Well, it's a lot of reading you read that. So you see how we went through each of these steps. And when we write this part of the book, it took us a lot of time because which part will go first? It's not as simple. You can look at the other books, it does not go that detailed, so we went into detail. So when we come back on Friday, and Alex is going to read the wave function part. And one thing that I do really like the code, when you read those things, especially Tobin, when you read, I really like you explain the Dirac brackets. Please say Dirac brackets, so that way that the audience will understand this Dirac brackets are left. That's called a bra. You usually put it, if you call it like like these brackets, you would, when you read it, it will be much better. You call the bra, there's a k. You call the bra k, and then h hat, and underscore the I like this, just so h sub I and hat like this. So that the bra, and then this part of k plus 1, whatever, and you say bra k, and then when you end here, you just k to k plus 1. Just so that way people know that's the left and the right brackets. If you want to have these intervals directly, you just bracket notation for intervals. So this part is just k over like that when you read it. Sounds good? So that looks more professional. Sounds good? Okay, that's it. Any questions before we close it? No question? Okay, if you guys have any questions about the homework, make sure you do let me know. So we'll see.